In year n, the 300th day of the year is Tuesday. In year n plus 1, the 200th day of the year is also Tuesday. On what day of the week did the 100th day of year n minus 1 occur? So the first thing I'm going to do is draw out a little bit of a calendar for this question. And let's start filling in our values. So the first thing they tell you is that in year n, the 300th day is a Tuesday. So the 300th day is this Tuesday. And we have to kind of work from there. So therefore, 301 is Wednesday, 302 is Thursday, 303 is Friday, and so on, right? Like that. But obviously, we're not going to plug them all in. We can go and keep adding sevens, because every 7 days it's going to be a Tuesday. So if we do that, you can easily do that in your calculator. Just type in +7 and just keep hitting equals. It'll get to 363. So that means the 364th day is a Wednesday, 365th day is a Thursday. And then after that, we get into the next year, which is year n plus 1. 2, 3, 4, like that. 5, 6, 7, 8, 9. Now, of course, we don't have to keep doing this. We just want to get to day number 200 and ensure that it is indeed a Tuesday. So similarly, you can just keep adding 7 to this 8 here. And if you do that, you'll eventually get to ... 197. And therefore, this is 198. And this is 199. And then therefore, this is 200. So the 200th day is a Monday. But the question told you that the 200th day is Tuesday. So what happened here? What did I do wrong? Well, I didn't do anything wrong. I just wrote 365. The only way this can work is if we have one additional day. That means that year n is a leap year. And as you know, leap years have 366 days. So everything gets shifted over. This is now 366, and this is now 1. You see what happened? And that is how we can make this question work. This becomes 7, this becomes 8, and so on. And then therefore, if we keep adding, this becomes 197, this becomes 198, this becomes 199, and finally our 200th day is indeed a Tuesday. All right? So that's the first part of the question. Now we got the second part of the question, which is what day of the week is the 100th day of year n minus 1? All right, so now we got to go backwards. Well, the good news is that year n is a leap year, so year n minus 1 is not a leap year, right? Because leap years come every 4 years, not a leap year. So n minus 1 has a standard 365 days, okay? So now we got to work backwards from 300. And similarly, if you just keep going backwards from 300, you, by a fact multiples of 7, you'll eventually get, 293, and so on, ... like that. You can do it in your calculator. You can subtract by 70 too to speed up the process. And if you do that, you'll get down to 13, and then you'll get to 6. So then you'll have 5, 4, 3, 2, and 1. And therefore, the Wednesday will be 365 of year n minus 1. But they want the 100th day. All right? So same thing. You got to keep going backward from 365. And you can always subtract by 70s. And if you do, you'll get all the way down to 106. All right? So you got 105, 104, 103, 102, 101, and finally 100. And that 100th day is a Thursday. So the answer to 25 is A. How many positive integers not exceeding 2001 are multiples of 3 or 4 but not 5? Okay, so we have 2001. When you divide by 3, it'll give you the number of multiples of 3, and that is 667, the closest integer value. 2001 divided by 3 is actually exactly equal to 667. And then now 2001 divided by 4 is a little more than 500, but we are looking for the number of multiples, so we're obviously going to be looking for just the integer values. So this represents the number of multiples of 3, and this represents the number of multiples of 4 between 1 and 2001. So this looks like a total of 667 plus 500. But there's a problem that we have counted a few of these twice. Which ones? Multiples of 3 times 4, which is 12. Multiples of 12 have been counted twice. So how many multiples of 12 are there, first of all? Well, same kind of scenario, 2001 divided by 12, and you take the integer value that's closest to that, and that is 166. So now the total number of integers that are multiples of 3 or 4 from 1 to 2001 is 667 plus 500, and we have to subtract the 166 that was counted twice. So therefore this is 1001 unique multiples of 3 and 4. All right, so now we've got the first part. Now we have to look at not multiples of 5. So of all of these numbers that we got, we have to take out the ones that are multiples of 5. So how do we do that? So of all the multiples of 3 and 4, we must now remove those that are multiples of 5. So let's start with numbers that are multiples of 3 and 5. And those numbers, since they are multiples of 3 and 5, they are multiples of 15. So very similarly, you take 2001 divided by 15 and take the integer value of that, and you get 133. That's how many numbers between 1 and 2001 are multiples of 15. So these are the bad guys. Now we have to figure out how many are multiples of 4 and 5. Remember, of all the ones that we figured out in the first part of the question, we have to now get rid of the ones that are also multiples of 5. Well, multiples of 4 and 15 are multiples of 20. So these are the ones that we have to get rid of. Of all the ones from 1 to 2001, you get rid of the ones that are multiples of 20, and this is about 100. So now, very similarly, like we did earlier, we have to get rid of doubles because we've overcounted some of these. Which ones have we overcounted? The ones that are multiples of 3, 4, and 5. So if you have a number that's a multiple of 3 and a multiple of 4 and a multiple of 5, that has been overcounted. So that essentially means multiples of 3 times 4 times 5, which is 60, have been counted twice. So we got to get rid of those. So that's going to be 2001 divided by 60. Take the integer value, and that gives you 33. So now finally we have 133, 133. So 133 plus 100, but then we have to subtract the multiples of 60 that were counted twice, and it gives you 200. This represents the unique multiples of 3 and 5 and the unique multiples of 4 and 5. So these are the ones that we need to remove. Remove from what? Our original list, which was 1001. So final grand finale of this question is you take the original list, which was multiples of 3 and multiples of 4, and subtract from it all of those numbers that are also multiples of 5. And therefore the final answer is 801. And that would be choice B. When 15 is appended to a list of integers, the mean is increased by 2. When 1 is appended to the enlarged list, the mean of the enlarged list is decreased by 1. How many integers were in the original list? So we've got a list of integers, a plus b plus c dot dot dot. We don't know how many there are. And if you take their mean, divide by the number, so I'll let the number be n, we're going to get a certain number. I'll call it m representing the mean. So now let's work with the information they gave us in the question. They're first saying that you take this list and you add to it 15. And if you do that, the mean increases by 2. Now, what is our new number of integers? It's n plus 1, because we've added one number. Then they say, when you take this enlarged list and you add to it 1, so you're taking this enlarged list and you're adding to it 1, then that mean decreases by 1. So it was m plus 2, so now it will decrease by 1, becoming m plus 1. And then how many integers do we have to divide by? It's n plus 2. All right? So these are the two equations that we will need to work with. So the first one becomes a plus b plus c dot 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 15 over n plus 1 is equal to m plus 2, right? And the second one is a plus b plus c dot 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 plus 16 is equal to n plus 2 is equal to m plus 1, like that. So these are our two equations that we have to work with, and we got these two equations based entirely on the information in the question stem. All right, so let's work with those. What can we do? Well, we can subtract one from the other, and that hopefully will allow us to eliminate at least one variable, or not. We'll see. There is really not much we can do, so because we have so many variables, we have a, b, c, and all that stuff. But if we can get rid of all of those, that's really going to help us. All right? So let's do that. But before I do that, I want to try to simplify this, because we have so many variables, it's going to get very confusing. Let's go back to the original one, and you'll see something very interesting happens. A plus b plus c dot 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 equals nm, right? I just cross multiplied. So instead of writing a plus b plus dot 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 and all that stuff, we can just put nm. So the first one really just becomes nm plus 15 over n plus 1. See what I did there? Instead of putting a plus b plus c, blah, 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 I just put nm. And that equals m plus 2. So this is our first equation. And then our second equation simplifies to just nm plus 16 all over n plus 2 is equal to m plus 1. So you see how that's much more cleaner. And now I can proceed with what I wanted to do originally, and it will be much better because we now only have two variables, n and m. So 1 minus 2, nm plus 15 over n plus 1 minus nm plus 16 over n plus 2 is equal to m plus 2 minus m minus 1. All right? So a lot of algebra here. So let's just do the right side. That seems to be the simpler one. That just becomes 1. And on the left side, we have to get a common denominator. So multiply top and bottom here by n plus 2 and n plus 15. And this other side, we have to multiply top and bottom by n plus 1, like that. And that will be all over n plus 1 times n plus 2. Okay, so far, hopefully you're with me. So let's multiply this all out. We have n squared m plus 15n plus 2nm plus 30 minus n squared m minus nm minus 16n minus 16. And I'll just cross multiply. It equals 1, but I'm going to cross multiply that with that. And I'll expand it too. Why not? N squared plus 2n plus n plus 2. All right? Just basic algebra here. No, nothing fancy. Hopefully things will start to cancel. This guy goes. Anything else that goes? Well, let's see. Let's start combining. 15n minus 16n gives you minus n. 2nm and minus nm gives you just nm. 30 minus 16 is 14. And then this side is n squared plus 3n plus 2. So hopefully no mistakes. Hopefully we're good so far. Let's put everything on one side. N squared. Bring the minus n over, and that becomes 4n minus nm, and 2 minus 14 is minus 12. Equals 0. Okay, what can we do now? I guess we can factor out an n. That'll give me n plus 4 minus m, and I'll bring the 12 over. And that's about as far as I can go. Okay, so how do you solve this? Well, because you have two variables, we have to use something called inspection. All right? So inspection basically means you have to plug in some numbers and see what happens. Well, 12 is what this all equals, and therefore n has to divide 12, right? Something times something is equal to 12. So 12 divided by n must be an integer, because what is n? N represents the number of integers, and m represents their mean. So, for example, just want to make sure, it's a list of integers, correct? And the mean is increased by 2, blah, blah, blah. But n is the number of integers. So n has to be an integer itself. So for example, if there's 15 integers, 20 integers, n is always going to be an integer. So what integers divide into 12? Well, let's see. How about 12? That divides into 12. So let's put n as 12 and let's see what we get. All right, if n is 12, then that means 12 is equal to 12 times 12 plus 4 minus m. So that means 1 is equal to 16 minus m, and therefore m is equal to 15. Okay? So now we've got n equal to 12 and m equal to 15. Is this right? Well, we have to verify it. We have to go back and verify it by plugging it into our equations, which were right here, these guys. These were our two initial equations, and we have to use those to verify our values of n and m. If they satisfy this, then we're good to go. All right? So we have to use those two. So I'll write them out over here so that they are ready for us. All right, let's go for it now. So let's use the first one here. First one and second one. Let's try to verify with the first one. nm plus 15, so that would be 12 times 15 plus 15 all over n plus 1, which is 13. This gives me 180 plus 15 all over 13, and that is equal to 195 over 13, which is 15. All right? Now the other part of it is m plus 2. m plus 2 is 17. So unfortunately 15 does not equal 17. So this is a dud. We can't go with that. That's okay. That's what trial and error is all about. So n can't be 12. Let's go with the next one. What else can n be? Well, what else is 12 divisible by? It's divisible by 6. So let's go with that. N is equal to 6. And therefore 12 would be 6 plus 4 minus m. So 2 would be equal to 10 minus m. So m would be equal to 8. So we got 6 and 8. All right? So let's use that number 1 to see if we are correct. nm, so we got 6 times 8 plus 15 all over n plus 1, which is 7. 6 times 8 is 48 plus 15 all over 7. So this is 63 over 7, which is 9. And that has to equal m plus 2. And m is 8 plus 2 is 10. So 9 does not equal 10, so that's a dud. All right, let's keep going. It can't be 12, it can't be 6. What else is 12 divisible by? It's divisible by 4, so let's let n equal 4. If n equals 4, we've got 12 is equal to 4. 4 plus 4 minus m. So this becomes 3, this becomes 8 minus m, and therefore m is equal to 5. N is 4 and m is 5. Let's see if we can do it right here. N is 4, m is 5. All right, so the first one would become nm, which is 20, plus 15, all over n plus 1, which is 5. This is 35 divided by 5, which is 7. And we want it to equal m plus 2, which would be 5 plus 2, which is 7. Great. So we verified that one. Now we got to verify number 2. nm plus 16, so 20 plus 16, all over n plus 2, which is 4 plus 2, which is 6. So we got 36 over 6, which is 6. And that has to equal m plus 1. m plus 1, m is 5. 5 plus 1 is 6. Perfect. So 6 is equal to 6. We have verified both of them. So the correct answer is n is 4 and m is 5. N represents the number of integers, I believe. Yeah, how many integers were in the original list? N is 4. So 25 is A. How many distinct 4-digit numbers are divisible by 3 and have 23 as their last 2 digits? So 4-digit number, 1, 2, 3, 4. So it's got to be anywhere between 1,000 and 9999 inclusive. This is our range, I guess. So the numbers have to be divisible by 3 and they have to end in 23. So 1023, 1123. I'm just writing the numbers that end in 23. And I'll just do this for the range 1000 to 1999, like that. So 423, 523, 623, 723, 823, 923. There you go. Now, we just have to do this once. We have to figure out the other part of the criteria. We fulfilled our first criteria, but they also have to be divisible by 3. So let's see. If it's divisible by 3, this one is. This one is no. This one is no. This one is divisible by 3. Yes, it's 441. This one is not. This one is not. This one divisible by 3. Yes, it's 541. This one no. This one no. And this one is divisible by 3. It is 641. Like that. So basically, it looks like if you keep adding 300 to each of these numbers, it will fulfill both of our criteria. You see what happened there? If I keep adding 300 all the way up to the very end, and the very end will be 9723, because that divided by 3 is 3241. Okay? So that basically are all of our numbers that fit both criteria. They have 23 as their last 2 digits, and they're divisible by 3. Now we have to count how many of there. Well, we got 10, 2, 3, 13, 2, 3, 16, 2, 3, 19, 2, 3, all the way up to the last one, 9723. So how many of these? Well, it's not as difficult as you think, because 1023 was just 341 times 3, correct? 1323 was 441 times 3. 1623 was 541 times 3. I hope you're seeing a pattern here. 1923 was 641 times 3, and so on, all the way up to 3241 times 3. So what was the pattern? We've got 3, 4, 5, 6. It'll be 7, 4, 741, 841, like that, all the way up to 3241. So basically all the numbers from 3 to 32, except for 1 and 32. Those are not there. So how many are those? Well, that's 30. So 30 is the answer to this question. Number 25 is B. A circle of radius 1 is internally tangent to 2 circles of radius 2 at points A and B, where AB is a diameter of the smaller circle. What is the area of the region shaded in the figure that is outside the smaller circle and inside each of the 2 larger circles? So this is our diagram, and we basically have to figure out the area of the shaded region. So first I'll give you the strategy, and then once I give you the strategy, I'll proceed. Area of the shaded region will basically be the area that is common to the 2 circles, subtract the small circle, which is going to be pi small r squared. Now, what area is common to the 2 circles? It's this one right here. That is common to both circles, and if we find that and we subtract from that the small circle, we will get the shaded region. Now, the good news is that the small circle has a radius of 1, so this part just becomes pi 1 squared, and this is just the area of the common region minus pi. So in the next part of the question, I will concentrate on finding the common area. So here's the diagram again, and I'm interested in finding the common region to these 2 circles that are identical. Now, these circles have certain properties, right? We know that they have both a radius of 2, and they basically have center points right here and right here. And if you were to draw a line from those two center points, they basically would join like that, and that line would have a length of 2. Why? Because it essentially represents the radius. Okay, so that's the first part of this diagram. The next part is I'm going to draw lines to make triangles. So I've got a line from there to there, a line from there to there, and very similarly lines on the other side like that. Now let's talk about these lines. What do they represent? This first line we already discussed was the radius of either circle. What about this line here? That's also the radius of this circle on the bottom, so that is 2. And then this line represents the radius of the top circle, so that's also 2. So therefore this is an equilateral triangle, and in a very similar way, that's 2 and that's 2. So there you go. Now to find the common region to these two circles, which I previously highlighted, it's basically this one right here, that region right there, we have a certain strategy. We have to find the area of the two equilateral triangles, and then we have to find the area of this region that I'm labeling as A. And there are 4 identical regions of that kind. So the area that is common to those two circles will be the 2 equilateral triangles plus 4 of those A's. So let's first proceed with the equilateral triangle. So each of those equilateral triangles basically looks like this that I just drew on the side. We've got side lengths of 2, and we therefore need to find the area. So to find the area, I'm just going to draw a perpendicular from one side to the other, like that. And that will therefore cut this in half. This will be 1 and this will be 1. And we can easily figure out this length by Pythagoras. Basically, if we call that height, it'll be h squared plus 1 squared is equal to 2 squared. And therefore h squared is equal to 4 minus 1, which is 3, and h is root 3. Okay, so therefore each of these equilateral triangles has an area as follows: 1/2 base, which is 2, times height, which we just figured out was root 3. And keep in mind that there's 2 of them, so I'll just multiply by 2, like that. Now I have to figure out my area for A. Now how do I do that? Concentrate on this region right here, from there to there, and then across the circle. That is a pi, correct? And that pi will allow me to figure out region A. If I can figure out the area of pi and then subtract from it the area of the equilateral triangle, I will get A. So how do I figure out the area of that pi? That pi is essentially just a segment of the area of the circle. A circle of radius 2, pi r squared. But how much of the circle? Well, remember this was an equilateral triangle, so this is 60 degrees. So 60 is what you would place here. And then, once you have that, you would subtract from it the area of the equilateral triangle. And that would give you A. So first let's just figure out the area of the pi. So this will be 1 over 6 pi times 4. So this becomes 4 pi over 6. And then to get A, I would take my pi, which is this whole region, and I would subtract from it this equilateral triangle. And if I do that, I will get the area for A. So A is basically the pi, which is 4 pi over 6. Subtract from it the area of the equilateral triangle, which is 1/2 base, right here, 2, times height, which is root 3. And therefore we've got 2 pi over 3 in lowest terms minus root 3. There you have it. And now we can substitute that into here. So AC will then become 2 root 3 plus 4 times 2 pi over 3 minus root 3, like this. And this becomes 2 root 3 plus 8 pi over 3 minus 4 root 3. And this becomes 8 pi over 3 minus 2 root 3. This is the area of the common region. So we'll take that and place that into the first part of the equation, which is right here. Area of the shaded region is the area of the common region minus pi r squared. And since the small r was 1, we got AC minus pi. What did we get for our AC? Our common region, we got right here, 8 pi over 3 minus 2 root 3. 8 pi over 3 minus 2 root 3. And then don't forget this minus pi. So we get a common denominator. And that will be 8 pi minus 3 pi, which is 5 pi over 3 minus 2 root 3. That is the area of the shaded region. And let's see the answer choices. 5 pi divided by 3 minus 2 root 3 for number 25 is answer choice B. A subset B of the set of integers from 1 to 100 inclusive has the property that no two elements of B sum to 125. What is the maximum possible number of elements in B? So we've got some sort of a set, and it obviously has numbers from 1, 2, 3, 4, ... all the way up till 100, 99, so on. And what they've basically said is that this is our full range of numbers, but we are not going to use all of them. We're only going to use a subset of numbers. And they don't tell us how many either. That's actually what we have to figure out, the maximum possible of numbers. And the rule is that when you finally do figure out what B is, that subset, no two numbers in that subset can be equal to 125 in terms of their sum when you add them up. All right, so for example, if one of them was 100, we can't have a 25. If one of them was 99, you couldn't have a 26. Does that make sense? Because that would be 125. That would be 125 if you added them. All right, so that makes me think that a lot of these big numbers are no good. So if we bring this list down to, say, 63, right? If you keep going here, 63 plus 62, that equals 125. So if I don't include 63 and I go down to 62, I think I should be okay. Because 62 plus any number less than 62, like even if it's 61, will be only 123. So that makes me think I've got to eliminate all the numbers that are from 63 ... all the way to 100. So these guys are all gone. And that just leaves me with 1, 2, 3, all the way up till 62. And therefore this subset would have 62 numbers in it. And I believe that's it for number 25. So the answer is C. Mr. Jones has 8 children of different ages. On a family trip, his oldest child, who is 9, spots a license plate with a 4-digit number in which each of the 2 digits appears 2 times. "Look, Daddy," she exclaims, "that number is evenly divisible by the age of each of us kids." "That's right," replies Mr. Jones, "and the last 2 digits just happen to be my age. Which of the following is not the age of one of Mr. Jones' children?" So we've got a license plate number that has 4 digits, and 2 digits are repeated twice. So basically something like this: AB, AB, or AA, BB, something like that. Okay? And this number is divisible by all the ages. And the last 2 digits, whatever they are the age of the father. All right, so I'm just going to look at the answer choices and work with that. If this number, whatever it is divisible by all the ages, then it's got to be divisible by all of these except 1, correct? So which one is it not divisible by? I'm not sure, but these all are even numbers, and we've got 2 odd numbers. So that makes me think that the number that it's not divisible by is one of those 2. Okay, well, I don't know. So let's say that 5 is the one that it's not divisible by. Okay? So if that is indeed the answer, that means it's divisible by all of these guys: 4, 6, 7, and 8. So what we have to first do is figure out the lowest common multiple of these numbers and work with that. Okay, well, 4 is 2 times 2, 6 is 2 times 3, 7 is a prime number, and 8 is 2 times 2 times 2. So the lowest common multiple of 4, 6, 7, and 8 will be, you have to use the 2 3 times. You have to always use the maximum number of times it appears. So it'll be 2 times 2 times 2. The 3 appears in a maximum of 1 time, and the 7 appears maximum 1 time. So this is my lowest common multiple: 2 times 2 times 2 times 3 times 7, which is 168. Now my number has to be some multiple of 168. Okay? And when I do that, the last 2 digits will represent the age of the father. And also, the number has to only have 2 digits in it, appearing in some order. It could be like this, or it could be BA, BA, something like that, okay? Or the only other way would be like BBAA. Okay, so we have to, in a very painstaking way, figure out this number here. But there's actually a clue in the question stem that you might have actually missed. His oldest child is 9 years old. So 9 also is going to divide our number. So they mentioned that for a reason. It's not just something they've said in passing. So instead of just 4, 6, 7, and 8, I'm going to include the 9 in there. And I'll find the LCM of that. And that will help me out a little bit better because it will be a larger number. Well, 9 is 3 times 3. And therefore the LCM this time, 2 appears maximum 3 times, so that's going to be the same kind of story. 3 appears a maximum of twice, so I'm going to use the 3 twice. And I think the 7 is the only other one. So now this is my LCM. And that is 504. So I think that helps. Makes us have to do a little bit less work. So now I've got to find a multiple of 504. Okay? Shouldn't be that bad. Let's see here. 504. I'll write them on the side here. 1008. 1512. I'll stop when I reach something that looks something like this or something like this. So far, nothing. 2520, 3024, 3528, 4032, 4536, 5040, 5544. There you go, 5544. That is in this form right here. Now let's see if it meets our criteria. First criteria is that it has to be divisible by all the ages. And we actually don't know all the ages, but all the ages that we do know, 9, 4, 6, 7, and 8, it divides those. We know that for a fact because we've basically got the LCM. Okay? So that's the first criteria. Second criteria is the number has to have only 2 digits, and each of those 2 digits has to be repeated twice. So the digit criteria is definitely met because the number is 5544. And any other criteria? Yeah, the last 2 digits have to be the age of the father. And I mean, 44 is definitely a realistic number for the age of a father. And there you go. That's the answer. So after all that work, which of the following is the age that is not one of Mr. Jones's children? Well, it's 5. So I got a little lucky there, and I chose the right one. So number 25, the answer is B. How many pairs of positive integers AB are there such that A and B have no common factors greater than 1, and A over B plus 14B over 9A is an integer? The first thing I would like to do is let A over B equal X, and that will help us solve this problem. So that makes this equal to the following: X plus 14 over 9 times 1 over X. Now, this is equal to some integer n. So I will transform this into what will be a quadratic equation. Multiplying through by x, I get x squared plus 14 over 9 is equal to n times x. Put everything on one side and multiply through by 9. We get 9x squared plus 14 minus 9nx is equal to 0. And therefore this is a quadratic equation. And in order to get the solutions, I'm going to have to use the quadratic formula. So x equals minus b, which is minus 9n, plus or minus the square root of b squared minus n squared, minus 4a, which is 9, times c, which is 14, all over 2a, which is 9. Now, x simplified becomes 9n plus or minus 81 n squared minus 504. All under the square root sign, and that's over 18. Simplifying this a little bit further, this gives me 9n plus or minus. I can bring out a 9, and that gives me 3 once I bring it out of the square root. And that leaves me with just 9n squared minus 56, all under the square root sign, all over 18. And simplifying even further, this gives me just n over 2 plus or minus 9n squared minus 56 under the square root sign over 6. Now remember, this is equal to a over b, and a and b are integers. So since a and b are integers, this will be a rational number. A rational number, of course, is any number that can be represented in the form a over b. And the only way that can happen is if this is not a radical, right? That has to be a number. And in particular, what we mean is that 9n squared minus 56 under the square root sign must be a rational number. And the only way that's possible is if what is underneath or inside the square root is a perfect square. So 9n squared minus 56 has to be some perfect square. We'll call it m squared. And now we will use this information to try to figure out what is n. Bring m squared over to the other side and factor, and you'll get 3n, m and m, plus or minus, like that. And that is equal to 56. Now what we have to do, we have to make a table and try to figure out all the possible values of this. Now, we've got to understand that these two numbers, when multiplied together, have to be equal to 56, correct? So I'll put 3n plus m here and 3n minus m here. Now I've got possible choices: 56 and 1, 28 and 2, 14 and 4, and 8 and 7. Now I can't put 7 and 8 here because 3n plus m has to be greater than 3n minus m. Right? It's got to be greater. So this is not going to be needed. We just have to work with these four. So let's do that. Let's work with those four and let's see what solutions we get. So for the first one, 3n plus m is equal to 56, and 3n minus m is equal to 1. Adding these, you get 6n is equal to 57, and therefore n is equal to 9.5. Now n, remember, has to be an integer, so this is no good. This does not give me any solutions. Next one, 3n plus m is equal to 28, and 3n minus m is equal to 2. Adding these, we get 6n is equal to 30, and therefore n is equal to 5. So this is definitely one of the solutions we are going to use to try to figure out a and b later. First, let's just complete this. In the next one, 3n plus m is equal to 14, and 3n minus m is equal to 4. Adding, you get 6n is equal to 18, and therefore is equal to 3. So that's another one that helps us. And then the last one, 3n plus m is equal to 8. 3n minus m is equal to 7. And this gives me 6n is equal to 15. And that would mean n is equal to 2.5, and that's not an integer. So 5 and 3 are my only values of n. So let's use those and figure out what we get for a over b using this equation right here. So for n equals 5, a over b becomes 5 over 2 plus this becomes 9 times 25 minus 56 all over the square root over 6, and this is plus or minus. So that gives me 5 over 2, 9 times 25 minus 56 is 169, and the square root of that is 13. So it's plus or minus 13 over 6. This gives me values of 28 over 6 and 2 over 6. And remember, we have to put this into lowest terms because A and B cannot have common factors greater than 1. So that becomes 14 over 3 and 1 over 3. So there we go. We've got ordered pairs, 2 of them. We've got 14 and 3, and we've got 1 and 3. Now let's do the exact same thing for n equals 3. A over b is therefore now going to be using this formula up here. 3 over 2 plus or minus 9 times 3 squared, which is 81. 81 minus 56 is 25, and the square root of that is 5. So 5 over 6. So this makes A over B equal to either 14 over 6 or 4 over 6. Okay? And of course we have to reduce that, so that's going to be 7 over 3 or 2 over 3 for A over B. And that means we got 2 more ordered pairs, and those are 7 and 3 and 2 and 3. So there you go. We got 1, 2, 3, 4 ordered pairs. And therefore, number 25, the answer is A. Michael walks at the rate of 5 feet per second on a long straight path. Trash pails are located every 200 feet along the path. A garbage truck travels at 10 feet per second in the same direction as Michael and stops for 30 seconds at each pail. As Michael passes a pail, he notices the truck ahead of him just leaving the next pail. How many times will Michael and the truck meet? So we have to first understand this question, and then we have to find out which points do the truck and Michael meet at. All right, so we will figure out Michael. We will figure out the garbage truck, G for garbage, and this is the time. So at the very beginning, time 0, Michael is at 0 in terms of his distance. Okay, so what I'm going to put in this column is the distance for Michael from his starting point. And the same thing for the garbage truck, the distance. Now the garbage truck gets a 200 feet, right? Yeah, 200 feet head start. Because the question tells you that as Michael passes a pail, he notices the truck ahead of him just leaving the next pail. So we are using that as sort of our time 0. So let's work with this. At 50, that's 50 seconds into it, how much distance does Michael cover? Well, he's 5 feet per second, so 250 feet. Now, the garbage truck is a little bit different. It's not continuous. Michael is continuous. He just keeps walking, never stops, apparently. But the garbage truck travels and stops for 30 seconds, all right? So for the first 20 seconds, it travels at a pace or rate, 10 feet per second. So 20 seconds, 10 feet per second, that's 200. So it was at 200, travels 200, so it's now at 400. Then it stops for 30 seconds and remains there. So that's why for this full 50 seconds, it's still going to be here. So that's a little bit tricky. Not super tricky, but, just have to think about that. All right, let's move forward. Now let's get to the next 50 seconds. Now the clock is running. The cumulative time is 100 seconds. Michael just keeps walking. He covers another 250 feet. Now he's at 500 feet. The garbage truck, same story, travels 200 feet for those first 20 seconds, stops for 30 seconds. So these are the distances now. So this should be 600, sorry. They did indeed travel 200, but we have to put a cumulative distance. All right, so far so good. No tricks. All right, let's go. 150 meters. Again, Michael is pretty straightforward. He's just moving along at the same pace. And so is the garbage truck, by the way. We just have to keep in mind that the garbage truck has to stop for 30 seconds. So this is 800 now. Like that. Okay? Now we get to something that's different, where Michael catches up at 200. He's at 1,000, and now the garbage truck is at 1,000. So he finally catches up to the garbage truck, and that's the first meeting point. All right? And now at this point, the question gets a little bit harder, because we have to now figure out when does this meeting point occur again. And so we can't go in 50-second intervals anymore. We have to kind of break it down a little bit. In the beginning, we were just doing 50-second intervals, and it was pretty straightforward. But now we got to, in a very, in my opinion, painful way, we've got to think, all right, so what happens now? When does the garbage truck leave? When does it stay? And all that stuff, right? Okay, so 240 seconds. 40 seconds later, Michael has traveled 40 times 5, which is 200. So Michael's up to now 1,200. Now, 40 seconds later, keep in mind that the garbage truck has traveled for 20 of those seconds. So 20 times 10 is 200. So again, the garbage truck is at 1,200. Okay? So this is another meeting point at 240. So as you can see, we have to now look at slightly different intervals. We can't go every 50. And that's what makes this question challenging. Now let's just say the 251, which is our standard interval. What happens? Well, Michael's at 1,250 now. The garbage truck is still at 1,200. Why? Because remember, it stops for 30 seconds. Okay? So far, so good. Now we have to go very slowly in terms of our intervals, because they're very close together. And we don't know what's going to happen. They're going to probably meet very quickly. 10 seconds later, Michael's traveled 50 feet, so he's at 1,300. But in 10 seconds, the garbage truck travels 100, so it's also at 1,300. So at 260, they meet again. All right, so you see what's happening here? We've got to be kind of a little bit more intricate in our time intervals here. So again, let's see. Are we going to meet any other way? Let's try 270 here. I'm just going to go up by tens now. At 270, we got 1,350, and we've got 1,400. Okay, that wasn't an interval. How about 280? At 280, we've got 1,400, and we've got, 1,400, because remember, the first 20 seconds, the garbage truck is moving. So it's moving from 250 to 270. But then from 270 to 300, it stops, right? Those 30 seconds. So there we go. We got another meeting point right here at 280 in terms of our cumulative time. Okay. All right, I'm getting tired of this. Hopefully we can end this sooner or later. 300, we're up to 1,500. And then 1,400 still, right? Now the garbage truck starts moving, but we got to be careful. Let's try 320. At 320, Michael is up to 1,600, and the garbage truck is up to 1,600. Great. So we got another meeting point. And then at this point, let's see, 350. And Michael is up to 750. The truck is up to 1,600. Right? Because the truck is still stationary. It doesn't travel for those 30 seconds. 400, Michael is up to 2,000. The truck is 1,800. 450, now what happens, if you notice, Michael is getting farther and farther away. The truck is now not going to catch up to Michael. Okay? So that's it. That's it in terms of meeting points. 2,500, 2,200. You see how the truck's just getting further and further in terms of a distance. Michael is getting farther away. So that's it. We were done with our meeting points. How many did we get? We got 1, 2, 3, or 5 of them. All right, so that's painful in my opinion. And therefore, number 25, the answer is B. Each face of a cube is given a single narrow stripe painted from the center of one edge to the center of the opposite edge. The choice of the edge pairing is made at random and independently for each face. What is the probability that there is a continuous stripe encircling the cube? Let's first draw a cube and then let's talk about this. And what I'll do, I'll try my best to label each face. So I'll put it in the top left corner. So I'll call this one, it doesn't really matter, but I just want to ensure that you understand 1, 2, 3, and then we'll call this face 4. And then this face I'll call the front face 5 and the back face 6. So I'll put a little F there for front and a little B for back. And then T I'll put for top, just so you know. And then this, of course, is the side. 4 is the side. And 3 is the bottom. Now the point of doing that is to illustrate that a stripe can only be formed if it goes around like that, right? That's one stripe. And similarly, another stripe could happen like this. And similarly, another stripe could happen all the way around like that. So, in terms of my numbering, that would be as follows. It would be either, so, face 1, 2, 3, 4. This scenario is what? 1, 2, 3, and 4. So the stripe is going to be like that all the way around. This scenario, F1, 5, 3, 6. F1, 5, 3, 6 is a stripe that goes all the way around like that. And then the final one, F5, 2, 6, 4. 5, 4, 6, or whichever way you want to write it, 5, 2, 6, 4, like that, okay? So there's 3 scenarios. Now each of these scenarios obviously has a certain probability, and we can calculate that. And once we do, we will add up those 3, and that will be our answer. So for the first guy, the probability of getting a stripe is we want the stripe to look like this. F1, F2, F3, F4, the stripe has to look like this on the top. So there's only 2 ways of drawing a stripe. Either you draw it like that or like this. So because there's only 2 ways and we want one of them, we want a probability of a half. That's basically what it'll end up becoming. For F2, similarly, there's only 2 ways of drawing a stripe, like that or like this. And of those 2, we want this one. Correct? So there's a half probability there. And these are all going to be multiplied because they all have to happen together. F3, in a very similar way, the stripe can happen either like this or like this. Of those 2, we want it like this. So a half there. And finally for F4, the stripe can be made like this or like this. And obviously we want it made like that. So therefore there's a half probability of the stripe happening like that, since it's 1 out of 2. And therefore this whole thing is 1 over 16. And in a very similar way, I don't think you need me to do this again, this whole scenario is also going to be 1 over 16, and so will this. So when you add them all up, you get 3 over 16. And that's it. So number 25, the answer is B. Let A be greater than 0. Let P at x be a polynomial with integer coefficients such that P at 1 equals P at 3 equals P at 5 equals P at 7 equals A, and P at 2, 4, 6, and 8 equals negative A. What is the smallest possible value for that A? Okay, where do we go from here? Well, one thing I immediately notice is that if you were to take each of these, right, for example, P at 1 is equal to A, and if you rearrange that, it just means that P at 1 minus A is equal to 0, correct? And very similarly, you can do that for every one of those. P at 3 minus a is equal to 0. P at 5 minus a is equal to 0. And P at 7 minus a is equal to 0. All right? So what we can immediately do is introduce a polynomial. Let's call it r at x. And we'll call that p at x minus a. And since p at 1, 3, 5, 7 minus a equals 0, that means that this polynomial has roots when x is equal to 1, 3, 5, and 7. So, since those are the roots, we can write it as follows: x minus 1, x minus 3, x minus 5, x minus 7. Correct? Now, those are not all the roots. I don't know what all the roots are. I just know some of the roots. So I can't just leave it at that. I also have to tag on a q at x, where q at x represents the remainder of the polynomial. I have no idea what that is. So keep that in mind. All right, where do we go from here? Well, we know that this r at x is p at x minus a. So let's just put that back in, because that's going to be very helpful for us, and the rest remains the same. Okay, now we're going to have some fun. Now is where we substitute these guys. P at 2, P at 4, 6, and 8. So when we do, we will get some interesting results. First, let's do P at 2. If we substitute 2 for x, we get P at 2 minus a is equal to 2 minus 1 times 2 minus 3 times 2 minus 5 times 2 minus 7. And then we have q at 2. And that is equal to minus a. Correct? So we have minus a. But I'd like to actually get a numerical value, so I will. When you do all this numbers, whatever, you get minus 15 q at 2 is equal to minus a. But be a little careful, because remember, p at 2 is minus a, but we are actually subtracting another minus a. So this is actually minus a minus a. So it's actually minus 2a. Not that it makes a big difference, but just to be complete and accurate. Now we do the exact same thing for p at 4. P at 4 minus a, we'll substitute that in. And if you do the math here, you get 9q4 is equal to minus 2a. And then, of course, we'll do the exact same thing for p at 6 and p at 8. And that is again going to be minus 15q6 is equal to minus 2a. And then finally, we do p at 8 in the exact same way, minus a, using this same equation up here. And if you do the math there, you get 105q8 is equal to minus 2a. All right. So what did we get here? We have a whole bunch of formulas. We got the first one, which is minus 15q2 is equal to minus 2a. Then we got 9q4 is equal to minus 2a. Minus 15q6 is equal to minus 2a. And 105q8 is equal to minus 2a. So all of these are equivalent. Now, for all of those to be equivalent, that means that these guys are all equivalent. Correct? So to figure out a, we really have to figure out the lowest common multiple of these numbers, which are 15, 9, 15, and 105. That's what this boils down to. Well, 15 is 3 times 5, 9 is 3 times 3, 15, of course, again, is 3 times 5. And 105 is 3 times 5 times 7. So the LCM, 3, we would have to use it twice, since it appears twice. We have to use it as maximum amount of time it appears. The 5 only appears once, and the 7 only appears once. So that is the LCM, 3 times 3 times 5 times 7. And if you do that, that is 315. And that is the minimum, because A is going to be something times 315, 315n perhaps. And this is minimized when n is equal to 1. And that, of course, gives a value of 315. So the answer to number 25 is B. Let T1 be a triangle with sides 2011, 2012, and 2013 for n greater than or equal to 1. If T at n is equal to ABC triangle, with D, E, and F are points of tangency of the incircle of triangle ABC to the sides AB, BC, and AC respectively, then T at n plus 1 is a triangle with side lengths AD, BE, and CF if it exists. What is the perimeter of the last triangle in the sequence Tn? So let's first create some triangle and talk about this. So here is our diagram. We've got this triangle, and we can label it, of course, A, B, C, and then we will label the points of tangency, D, E, and F. D is here approximately, E is here, and F is here. And then, because of this triangle being tangent, we can draw lines from the center to the vertices like this. And what that allows us to do is figure out that some of these distances will be equal. So for example, if I label A to F as X, and A to D will also be X, because those are similar triangles. And very similarly, if I label B to D as Y, then B to E will also be Y. And if I label F to C as Z, then E to C will also be Z. So we got a few equations here. The first is X plus Y in my first triangle is 2011. And then X plus Z in my first triangle is 2012. And Y plus Z is 2013. Now we want a general formula for what will X, Y, and Z be for each T to the N. What will it be for, well, T1 we know, but what will it be for, say, T to the N? And then we can calculate it for T2, T3, T4, and then eventually we'll get to a T that doesn't exist in the sense that you can't make a triangle. Because in any triangle, remember, we have a fundamental triangle inequality that two sides have to be greater than the third side. Okay? So let's first figure out this, solve for X, Y, and Z. But I want a general formula. I don't want numbers. I mean, I do want numbers, but I want a general formula that will help me get numbers for all of these. So to do that, I will let just something equal 2012. So I'll let, say, P equal 2012. If that's the case, this becomes X plus Y is equal to P minus 1, X plus Z is equal to P, and Y plus Z is equal to P plus 1. And then now I can solve. So solving these, let's see, the first one I can do, I can subtract. I can subtract this equation from that equation, and if I do, I get Y minus X is equal to 1. And then now I can take that equation and add it to that equation, and that gives me 2Y is equal to P, and therefore Y is equal to P over 2. So that's my first general rule. Then I can continue like this. For example, just substitute that into there, and that should be sufficient to give you X. X is basically going to be p over 2 minus 1. And that's it. So that's my general formula for x. And then z, I can get again by substituting into here, let's say. So that will give me p over 2 plus z equals p plus 1. So that means z is equal to p over 2 plus 1. And now I can start making my list of t's. So using these three general formulas, 1, 2, and 3. So the first one, t1, I have xyz as p over 2 minus 1, p over 2, and p over 2 plus 1. And remember, p, we had made the substitution as being equal to 2012. And when you do plug that in, you get values as follows. This is, t2. And that will give you values of 1005, 1006, and 1007. So now we turn our attention to t3. This time, we're not using p equals 2012. We're using this middle number, 1006. If you do that, you get 502, 503, and 504. And you continue like this, and you get all these values for T4, T5, all the way up to T10. And then when you get to T11 and you use these standard formulas with the right substitutions, you will get the following. 247 over 256, 503 over 256, and 759 over 256. And this is not possible because the triangle inequality does not stand up. This would have to be greater than those two, would have to add up to be greater than the third, and in this case it's less than. So this is the last triangle that actually works with the triangle inequality. So now all we have to do is find the perimeter of that, and the perimeter of that, of course, you just add up the three sides. So 375 over 128 plus 503 over 128 plus 631 over 128. And then when you add all those, you get 1509 over 128. 1509 over 128 is choice D. A bug travels from A to B along the segments in the hexagonal lattice pictured below. The segments marked with an arrow can be traveled only in the direction of the arrow, and the bug never travels the same segment more than once. How many different paths are there? Well, this is a rather challenging question. This diagram colors the paths. You got red, black, blue, black again, green, black, and orange. And we have a very nice explanation. So I'll just go through it and then you can kind of verify it. There is one way to get to any of the red arrows. There's only one way to get there and only one way to get there. From the first top red arrow, so this one, there are two ways to get to each of the first and second blue arrows. So what are those two ways? Well, from here, obviously that's one way to get to that first blue arrow, but then you can also go like this, which is sort of a, like this, which is sort of a roundabout way of getting to that blue guy. So that takes care of this one and this one. From the second bottom red arrow, which is this one, there are three ways to get to each of the first and second blue arrows. So one way, of course, is this path. Another way is this path right here, going back like that. And then another way is this path right here. So there's three ways. So in total, there's 5 ways to get to each of the blue arrows. So This is very important. Then from each of the first and second blue arrows, so this guy and this guy, there are 4 ways to get to each of the first and second green arrows. So 4 ways to go from here to here. So for example, here's one way. Here is another way, that's 2. And then here is a third way. And here is a fourth way. It's a long way, but it's a fourth way. So that takes care of that. From each of the third and fourth blue arrows, so these guys, there are respectively 8 ways to get to each of the first and second green arrows. So they're saying from here to go to here, or here, 8 ways. And I'll let you do the counting. So that takes care of this. So in total, there's 5, which is up here, plus 4, plus 4, plus 8, plus 8, which is a total of 180 ways to get each of the green arrows, to get to each of the green arrows. So they're counting the 4 up here twice, right? Because you have to get to the first and second, and then the 8 here to get to the first and second green arrows. Okay, so so far we're only just doing these 2. So I guess at the end we're going to double it. And then finally, from each of the first and second green arrows, there are 2 ways to get to that first orange arrow. So obviously this is one way, and this is another way. And then from each of the third and fourth green arrows, these 2 guys, there are 3 ways to get to that first orange. So you take that 120 that you got, and then you multiply it by 2 plus 2, 2 from there for the first and second, and then 3 for the third and fourth. That's why you got 2, 2, 3, and 3. And that you have to multiply by that 120. And when you do, you get 1200. But that's only talking about the first orange. The second orange one has the exact same pattern. So you have to multiply that 1200 by 2. And that's why you get this number 2400 for the total ways to go from A to B. So I encourage you to go through this once again and just manually figure out all the paths. There's only one big one, and that's this 8 right here. The rest are either 2 or 3, so it's actually not so bad. And another thing I just want to mention is that because in this question one of the factors is 5, the final answer has to be a multiple of 5. Now if you go back to the original question, the only answer choice that is a multiple of 5 is E. So if you're rushed for time and you only got, say, to here, and you say, well, I know that there's 5 somewhere as a factor of the final number, you can just say, okay, well, of the answer choices, the only one that is a multiple of 5 is 2400. So either way, the answer is E for number 25. Bernardo chooses a 3-digit positive integer n and writes both its base 5 and base 6 representations on a blackboard. Later, Leroy sees the 2 numbers Bernardo has written. Treating the 2 numbers as base 10 integers, he adds them to obtain an integer s. For example, if n is equal to 749, Bernardo writes the numbers 10444 and 3245, and Leroy obtains the sum 13689. For how many choices of n are the 2 rightmost digits of s in order the same as those of 2n? This question, I'm going to break it up into 2 scenarios. The first is we're going to just look at the units digit, and then once we have completed that discussion, then we'll look at the tens digit, and then we'll combine the 2 because they want you to figure out the 2 rightmost digits. So that would be the units digit and the tens digit, correct? So let's explain this first with just the numbers they've given in the question. They have chosen initially a number 749. And then what they did is they created the base 5 and base 6 numbers. So 10, 4, 4, 4, base 5 is 749. And then they found the base 6 representation of 749. And then what they did is they added up those two numbers. And when they do, they get a sum of 13689. And what they're saying is then you have to take 2n. So in our case, 2n would be 1498. And they're saying that the last two digits, the last two or the two rightmost digits of s, which in this case are 89, are the same as those of 2n. In our example, or the example with the numbers in the question, it's not the same. This is 89 and that's 98. But they're saying they want you to come up with values of n so that these two digits for s match up with those two digits for 2n. Okay, so that's what they're asking for. Well, how do you do that? Is you've got to look at mod. And some of you are familiar with mod and some of you may not be, but if you're not, you definitely need to be to understand this question, but I'll try to walk you through it. Let's say you have a number n, and they're saying that it's a 3-digit, so we have first digit, second digit, third digit, and let's say the third digit is an a. And then 2n, it might be a 4-digit number, most likely, or it may not be, but whatever it is, whether it's 3 digits or 4 digits, its last digit could be a 2a, right? Depends what it is, but let's just keep it 2a for now. And then this is all in base 10. So this was our base 10 because n was always given in base 10. But then we have to also look at the consideration or scenario of base 5 and base 6, right? So in base 6 we have some number. I have no idea what that number is, but I'll just write the last digit. Let's say it's a b. And then base 6, again, I have no idea, so I'll just denote the last digit as a c. I'm only looking at the units digit in this part of the question's explanation. Now I have to look at s. S is going to be this number plus that number. So whatever s is, the very last units digit could be b plus c. Now what's important to understand is some parameters. B, because it belongs to a base 5 number, b has to be less than 5, right? That's what it means. In base 5, you can only have numbers 0, 1, 2, 3, and 4. In base 6, you can only have numbers 0, 1, 2, 3, 4, 5. So c must be less than 6. So if you go back to the question, they want the last digit, well, they want the last two, but I'm just looking at the last digit of 2n to be the same as the last digit of s. Okay, so that basically means that we want 2a to equal b plus c. Well, looking at these parameters, the largest b can be in terms of an integer value is 4. It has to be less than 5. The largest c can be is 5 because it has to be less than 6. So the largest that 2a can be would be 4 for b and 5 for c, so that's 9. So that's the largest it can be. But a has to be an integer, so a has got to be less than or equal to 4. All right, so I hope that makes perfect sense. So that's a parameter for a. Now we have to get into the next part of the discussion, which is looking at mods. So here we go. N is equivalent to a mod 10, right? What that means is that when you take n and you divide by 10, the remainder is a. And if you look at this number here, that means that b, if you were to write it as mod 5, would also be equivalent, because if you take that number and divide by 5, it would give a remainder of b. And that is also equivalent to c mod 6 when you consider that number right there. So what I've written here is just basically saying that if you were to divide the number by 10, you would give a remainder of a for n. And if n is divided by 5, it gives a remainder of b. And if n is divided by 6, it gives a remainder of c. Now, the value of n, just by basic definition, if you look at this number right here, is written, since it's base 10 times some value plus a, right? So, since a is the remainder, when you divide by 10, and then you can break this up into 5 times 2k plus a, and then now if you were to take the remainder when you divide by 5, it would just be a. So I can write n is congruent to a mod 5. All right? But that's identical to this right here. N is also congruent to b mod 5. So that makes me conclude that a must be equal to b. Since this is the same as that, that means a is equal to b. Then what I do is I plug this into my original condition. So I have 2a is equal to b plus c, but b is equal to a. So that means 2a is equal to a plus c, and that means c is equal to a. So a is equal to b, a is equal to c, so that means a is equal to b is equal to c. And that is how you are going to get values that satisfy this. When they're all the same, they will have the same units digit. But what are the numbers? Well, a has got to be less than or equal to 4. So this is true for a equal to 0, 1, 2, 3, and 4. So there's 5 possible values, right? 0, 1, 2, 3, and 4. So 5 possible values of a. So that gives me 5 scenarios. So we are complete with the first part, which is the units digit. Now we get into the second part, which is the tens digit. And then once we have that, we can combine it with the units digit's 5 values, and we should get the answer. So just to recap, the units digit of 2n will equal the units digit of s for these 5 values of a. A equals 0, 1, 2, 3, and 4. All right, now we move on to the tens digit, and again, we have to look at this n. And n is congruent to a, but we have to now look at the tens digit. So we have to make this a little bit, we have to extrapolate it into bigger numbers. But where do I start? It's a 3-digit number, right? But which numbers do I look at? Do I look at every 3-digit number from 100 to 999? Well, that's probably not a good strategy because we don't need to worry about a lot of them. We only need to look at numbers that are the lowest common multiple of our bases. And our bases are 10, 5, and 6. So that is the same as writing a mod. The lowest common multiple of 10, 5, and 6 is 30. So we only have to look at those ones. And if we do, we will be able to get what we're looking for. So n is congruent to a mod 30. So if we try a equal to, say, 0, that's the equivalent of 0 mod 30. So those are numbers that are multiples of 30. So for example, n equals 120, n equals 150, right? I'm starting with the lowest possible 3-digit number, 180, 210, 240, and so on, right? All the way up until the very last one, which would be 990. And then if a is 1, then those numbers would be like 121, 151, and so on, 181, 211, 241, 991. If a is 2, it'd be 122, and so on. If a is 3, it'd be 123, and so on. And if a is 4, it would be 124, and so on. And those are the only ones we need to worry about, because if you go any higher, we would get numbers that wouldn't match this scenario of giving a common mod for 10, 5, and 6. So these are the only numbers we need to worry about, but there's a lot of them. So there's quite a few numbers we will have to consider. So let's start our list and let's make our comparison. So we are looking at, first and foremost, 2n, and of course that's to the base 10. Then we're looking at n to the base 5, and then we're looking at n to the base 6. Correct? And for 2n to the base 10, let's start looking at just the tens digit. So I'm only going to write the tens digits here. So here we go. And we can start, of course, with these numbers right here in this column. So 120, if you multiplied it by 2, because we're looking at 2n, is 240. 240, the tens digit, obviously, is 4. So I'll put the 4 right there. And then I look at the next one, 150, but that's n multiplied by 2, I get 300. And 300, the tens digit, is 0. 180 is the next one. Multiply that by 2, you get 360, and the tens digit is 6. 210, if you multiply it by 2, you get 420, and the tens digit is 2. 240, if you multiply by 2, is 480, and the tens digit is 8. The next one is 270, that gives 540, and the tens digit is 4. And what you'll notice, this just repeats itself, 4628, 4628, like that. And we are looking at all the numbers until 990, so that's 30 of them. So I've got to write this out so that there's 30 of these numbers. So 4628, it's got to be written 6 times. Okay, so that takes care of the tens digits for 2n. Now let's look at the tens digits for n to the base 5. That's going to take a little bit of math, so I'm going to do it down here. The first number we're looking at is 120, right? When that n is equal to 120. But in base 5, if you write 120, it's 440 base 5. So the tens digit there, as you can see, is a 4. Then we're looking at 120, but in base 5, that is 11005. So the base 10 is the base 5 number is 1100. 1100, the tens digit there is a 0. And then the next one is 180. In base 5, 180 is 1210, and the tens digit there is a 1. Then we look at 210, and in base 5, that is 1320, so that is a 2. And then we look at 240, and the base 10 is 1432, so the tens digit there is a 3. So this pattern actually repeats itself, so that's good news for us. We can just write it all out like this, 40, 1, 2, 3. And I'm trying to match these up because we, of course, have to match them up at the end. We have to get a scenario so that the tens digits add up. So 40, 1, 2, 3. Okay, now we get to n to the base 6. For the same numbers, when n is 120, In base 6, it's 320. So the tens digit there is 2. When n is 150, in base 6, it is 410. So that is 1, the tens digit. When it's 180, it's 500. So that's a 0 for the tens digit. 210 is 550. So that gives me a tens digit of 5. 240, the tens digit will be, it's 1040. So the tens digit will be 4. And interestingly, this doesn't have a pattern after 5. It has a pattern after 6, which makes the question even more challenging. And that's 1130 to the base 6, and that would make it a 3. So this is the pattern that repeats. 210, 543. So I've got to carefully write this out. 210, 503, 210, 503, 210, 503, 210, 503. All right, now, finally, now we have to do the comparison. So what are we doing? Let's remind ourselves. We're trying to match so that the tens digit of 2n is equal to the tens digit of n to the base 5 plus the tens digit of n to the base 6. Correct? So let's see how many of these actually match up. This one matches up right here. As you can see, this will hold true for the tens digit. This one also matches up. And then this one does. And then I believe this one, these are all zeros. And this one also. 5, 1, and 6. So we have 1, 2, 3, 4, 5. So we have 5 cases here. 5 cases where the tens digit matches up. So remember we had 5 up there for the ones digit right here. 5 possible scenarios. And then for the tens digit we have also 5. So the total is 5 for the units digit, 5 cases. And then we have 5 for the tens digit. So we have to multiply them because each of them can combine with the other. And when you do, you get 5 times 5, which is 25. 25 total cases where the tens digit and the units digit match. And therefore, the answer to this very challenging problem is 25, and that is choice E. In a small pond, there are 11 lily pads in a row, labeled 0 through 10. A frog is sitting on pad 1. When the frog is on pad n, where n is greater than 0 but less than 10, it will jump to pad n minus 1 with probability n over 10 and to pad n plus 1 with probability 1 over n over 10. Each jump is independent of the previous jumps. If the frog reaches pad 0, it will be eaten by a patiently waiting snake. If the frog reaches pad 10, it will exit the pond, never to return. What is the probability that the frog will escape being eaten by the snake? So we have pad 0, 1, 2, all the way up until pad 10. Now, a really helpful thing to realize in this question is that the frog starts here, right, at pad number 1. But if the frog reaches pad 5, then, because of the symmetry of this diagram, it has half the probability, 50% of going all the way here, and 50% probability of going there. So that's very important. So by symmetry, if the frog reaches pad 5, the probability is of half of going to pad 10, and the probability is 1/2 of going to pad 0, where the snake is. So we are interested in him obviously going away and escaping. So before we jump right in, let's create just a few examples of what can happen. So he starts here, and based entirely on the question, the stem, and the information, if he is going to go here, that happens with a probability of 9 over 10. And if he goes here, it happens with a probability of 1 over 10. That's entirely based on the question. If we keep going, and we are now here, pad 2, the probability of going back to pad 1 would be 2 over 10, and the probability of going to pad 3 would be 8 over 10. If we are at pad 3, the probability of going to pad 2 would be 3 over 10, and the probability of going to pad 4 is 7 over 10. And then similarly, if you're at pad 4, the probability of going to pad 3 would be 4 over 10, and the probability of going to pad 5 would be 6 over 10. All right, so now we have to combine all of these. So if you're at pad 1, and let's give a definition first. Let pk represent the probability that the frog escapes if it is on pad k. So, based on that definition, P1 is the equivalent of 9 over 10 P2, right? Because he was here, and in order for him to go there, the probability is 9 over 10. And very similarly, P2 is going to be calculated as follows. First, we have to figure out 2 over 10 P1, right? 2 over 10 P1 plus 8 over 10 P3. There we go. And then P3 is going to be 3 over 10 P2, right? 3 over 10 P2 plus 7 over 10 P4. And then P4, that is going to be 4 over 10 P3, right? 4 over 10 P3 plus 6 over 10 P5. And then finally P5, well, we get that one for free since we had established that the probability of escaping when you reach pad number 5 is a half. Because of the symmetry of the diagram, it's a half to go there and a half to go there to 0. So P5 is actually a half. So now what we have here basically is a system of equations. We have 4 variables, P1, P2, P3, P4, and we have 4 equations. We actually have 5, but the 5th one just gives me a direct value for P5. So you solve these system of equations, and you guys know how to do that. And when you do, solving this, you get P1 equal to 63 over 146. So that basically means that because he starts off on pad number 1, 63 over 146 is the probability that the frog will escape. And therefore, number 25, the answer is C. A rectangular box measures A times B times C, where A, B, and C are integers, and 1 is less than or equal to A, which is less than or equal to B, less than or equal to C. The volume and the surface area of the box are numerically equal. How many ordered triples ABC are possible? All right, well, if the volume and the surface area are equal, that basically means that ABC is equal to 2AB plus 2AC plus 2BC. Divide everything by 2ABC, and when you do, you get 1 over 2 is equal to 1 over C plus 1 over B plus 1 over A. Now, keep this in mind. This inequality is very important, that 1 is less than A is less than B is less than C, or equal to. So that basically means that A must be greater than 2, because these are all positive. A, B, and C are positive. And the only way that 1 over A plus these guys can be equal to a half is if A is greater than 2. If A was equal to 2, there's no way you could add two positive numbers and have it be half. And similarly, if a was 1, there's no way that could happen. If it was negative, you could, but a, b, and c are all positive. So a's got to be greater than 2. And that basically means that a has to be greater than or equal to 3. Now, from that inequality, 1 is less than or equal to a, less than or equal to b, less than or equal to c. If we flip it, we get the following. You get that 1 over a is greater than or equal to 1 over b is greater than or equal to 1 over c. So that means that 1/2, which is equal to 1 over c plus 1 over b plus 1 over a, if c is less than 1 over a, right? 1 over c is less than 1 over a. That means I can write it like this. This is less than 1 over a. Similarly, this is less than 1 over a. And then this is 1 over a. So this can be written like this, which is of course the equivalent of 3 over a. So 1/2 is less than or equal to 3 over a. So if you cross multiply, you get a is less than or equal to 6. So we have our parameters now. If we combine them, a has to be either greater than or equal to 3 or less than or equal to 6. So a can only be 3, 4, 5, or 6. Those are my values for a. And now I have to figure out values for b and c to get the ordered triples. Okay, so here we go with b and c. If a is equal to 3, we need a system to figure out the values of b or c. You can substitute it in here and figure it out, but that would take a little bit of casework or might be very time consuming. So what I'll do is try to come up with something that I think might help and proceed from there. And that equation I'll come up with is as follows. From the top, we have ABC is equal to 2AB plus 2AC plus 2BC, right? What we can do is bring one of those over, say 2BC, and that leaves me with just 2AB plus 2AC, and then we can factor this guy, factor out a BC, and when you do, you get A minus 2, and this one you can factor out a 2A, and you get B plus C. So this equation hopefully will help. So we will use this throughout. So when A is 3, we get basically BC is equal to 6 times B plus C. And then if we do a little bit of fancy algebra, bring this over like this, and then if we try to factor, it can be facilitated by adding 36 to both sides, and we can factor into B minus 6 times C minus 6 is equal to 36. And then this will allow us to get our ordered triples A, B, C with a little bit of experimentation. And when you do, well, the A is 3, so we can use, say, 7 and 42. I mean, I hope that when I put it in that form, it makes it easier to figure out B and C. We got 8 and 24, 9 and 18, 10 and 15, and 12 and 12. And of course, the A's are always going to be 3 here. So I got 5 ordered triples here. All right, let's proceed in the exact same way, but this time for A equals 4. If A equals 4, again, using this formula down there, we get 2BC is equal to 8B plus C. And then if we divide through by 2, of course, BC is equal to 4B plus C. Put everything on one side and do a little bit of factoring. It will help us factor if we add a 16 to both sides. And when we do, we get B minus 4 times B minus 4, C minus 4, I should say, is equal to 16. So now let's figure out our ABCs here. And again, the hope is that doing this fancy algebra helps you figure out the ordered pairs. And you get 5 and 20, 6 and 12, and 8 and 8. And of course, A here is 4. So I got 3 ordered triples. Moving right along, we got A equals 5 now. And again, using that formula down there, we get 3BC is equal to 10B plus C. And therefore, if we multiply both sides by 3, we get 9BC is equal to 30B plus C. And therefore, 9BC minus 30B minus 30C. And then if we add 100 to both sides, it helps with the factoring a little bit. And when you do factor, you get 3B, 3C, 10, and 10. And again, the hope is that factoring will help you recognize the triples. And in this case, there's only one that is 5 and 10. And the value for A is 5. And finally, we have one last one. That is A is equal to 6. And when A is 6, it becomes 4BC is equal to 12B plus C. And that becomes BC is equal to 3B plus C. And again, BC minus 3B minus 3C. If we add a 9 to both sides, it helps us factor. Becomes B minus 3. C minus 3 is equal to 9. And let's see what we get for our ABC. I think we get just 6 and 6 is our only possible way of doing this. And of course our A is 6. So there we go. We have 5 here, 3 here. That's 8, 9, and 10. We have 10 ordered triples. So number 25, the answer is 10, which is choice B. Let f of x equal the sum from k equals 2 to 10 of kx bracket minus k times bracket x, where bracket r denotes the greatest integer less than or equal to r. How many distinct values does f of x assume for x greater than or equal to 0? So for example, 5.6 bracket is equal to 5. It's the greatest integer less than or equal to the value inside the bracket. So what we have here is something that we need to figure out. How does this behave? So what you do is you look if there's any sort of a periodic nature to it. And if so, what is that? And what is the period? So let's see what we get for x plus 1. This would be k equals 2 to 10. And it would be kx plus 1 minus k x plus 1, like that. And this is k equals 2 to 10. And if you multiply this, you get kx in the bracket plus k in the bracket. And then this side becomes minus kx inside the bracket minus k inside the bracket. Well, this guy and this guy cancel, so all you're left with is k equals 2 to 10 of kx inside the bracket minus k times x inside the bracket. Well, this right here is pretty much f at x. So it's really just k equals 2 to 10 of f at x. Well, actually, the whole thing is f at x. So I don't even need to put the summation like that. That's pretty much what I meant. So what this tells me is that f at x plus 1 is the same as f at x. So that means f at x is indeed periodic. And it has a period of 1. So basically, when you go from 0 to 1, let me just draw something basic. This is certainly not what it looks like, but just for the sake of explanation, let's say you have 0 to 1, right? And the graph looks something like that. Well, that means it's going to look like that every single period of 1. So from 1 to 2, again, it would look like that. From 1 to 2. And then 2 to 3, it'll look like that. So that's what they mean, where f is periodic with a period of 1. Another example that probably a little bit closer to your memory is those sine and cosine graphs. You remember how they are basically the same? And if you remember, those are the same. This is, for example, sine x. And as you can see, it's also periodic, meaning it repeats itself. And its period, if you remember, what is that point? 360 degrees, or sometimes also referred to as 2 pi in radians. So that's what we figured out with this calculation here. Okay, so now we must move forward with this important piece of information. That means all the values that you need to know for f of x are really just between 0 and 1. Just like how in the sine graphs, all the values you really need to know would be between 0 and 2 pi, because the rest is always the same. So in a sentence, the number of distinct values of f of x assumed that f of x assumes is the same as the number of distinct values that f of x assumes in that period from 0 to 1. All right? So hopefully that makes perfect sense. And for this interval, the value of bracket x would be 0, right? Because all those numbers are decimals, like 0.3, 0.7, and if you take the greatest integer less than it, it's 0. So that means that this whole thing, which is f of x, really just reduces to the following: 2 to 10. Since x is going to be 0, this becomes 0. So all you're left with is just that kx in the bracket. And that's it. And for this function, which is of that form, that function will have a number of values, and those values can be calculated by substituting values of x, and those values of x obviously have to be between 0 and 1 inclusive. And if you look at this carefully, you'll see that they are going to pretty much be all fractions between 0 and 1. And since k is going from 2 to 10, you'll be able to calculate that those fractions are these ones right here. And these are the distinct values. There's going to be some repeats, but the repeats have been taken out. And that totals 31. And then you also have to add one more value when x is 0. And therefore, that gives you 32 distinct values. And the values really that we were substituting were anything of the form x is equal to 1 over k, or 2 over k, or 3 over k, ... all the way until you got to k minus 1 over k. Just in case you're wondering, how did they come up with these fractions? And in our question, k was from 2 to 10, as you can see from the summation. So 32 is the answer to this challenging question, and that would mean that number 25, the answer is A. Last year, Isabella took 7 math tests and received 7 different scores, each an integer between 91 and 100 inclusive. After each test, she noticed that the average of her test scores was an integer. Her score on the 7th test was 95. What was her score on the 6th test? All right, there's 7 different scores. So that means the sum of all the 7 scores, the largest it could be and the smallest it could be are as follows: 91 plus 92 plus 93 plus 94 plus 95 plus 96 plus 97. That's the smallest. And then the largest would be 94 plus 95 and so on. So adding these up, the sum is going to be 658 on this side and 679 on this side. And this sum must be divisible by 7 because remember, when you take the average, it has to be an integer. So if you take the average of 7 numbers and you divide by 7, that has to be divisible by 7 in order to give an integer. That's why we know that this sum has to be divisible by 7. Well, the only numbers that are in this range that are divisible by 7 are 658, 665, 672, and 679. Okay, so we narrowed it down to 4. But when we get to the 6th test, we know that since the 7th test was 95, the sum of the first 6 tests would be these numbers minus 95. So S minus 95 is basically going to be as follows: 563, 570, 577, and 584. These are the sum of the first 6 tests. Now this has to be divisible by 6, right? That's the only way you can get an integer. Now which one of these is divisible by 6? The only one is this one. So that means the sum of the first 7 must have been 665. All right, so let's talk about this first set, second, third, fourth, fifth, sixth, and 7th. This is given as 95. And the sum of these guys is 570. And then the sum of these, the first 5, has to be divisible by 5. And the only way we can do that is to put here either 95 or 100 and test it out. You'll see if we put there 95, then you subtract from 570 95 and you'll get 475, which is indeed divisible by 5. If you put 100, you will get 470, and that's also divisible by 5. So this 6th number is either 95 or 100, and of those two, the only one listed in the answer choices is 100. And therefore, number 25, the answer is E. Let x bracket denote the greatest integer less than or equal to x. How many real numbers x satisfy the equation x squared plus 10,000 x bracket is equal to 10,000x? So we have x squared plus 10,000 bracket x is equal to 10,000x. Let's bring the x squared to the other side. So this side would become root x is equal to 10,000 x minus x squared, and therefore now I can divide through by 10,000, and it's going to leave me with just x minus x squared over 10,000. All right, now what is x? I am not sure, but x is an integer part plus a fractional part, correct? So therefore, if I take the bracket x, it becomes just the integer part. That's basically the definition. So for example, 4.3, if that's x, if I take the bracket of that, it just gives me 4. So substituting that in here, this becomes I. This is I plus f, and this is just, I'll just leave it as x squared over 10,000 for now. Now the i's cancel on both sides, and therefore if I bring the x squared over, I get the fractional part is equal to x squared over 10,000. Now the fractional part, obviously it's between 0 and 1. So that means that this x squared over 10,000 is obviously less than 1, but greater than or equal to 0. Multiply through by 10,000 and we get x squared is less than 10,000 or greater than or equal to 0. And therefore, x is going to be between 100 and negative 100. And therefore, x could be minus 99, minus 98, dot, 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 all the way to 0, and then dot, 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 all the way up until 98 to 99. Now that gives me, if you count up those integers, 199. And for each value of x bracket will correspond to one value of x. Now this question is a little confusing because x is a real number, right? Real number x. X, they don't specify as an integer. X bracket is an integer. But apparently, for every value of x, you get one corresponding value of x bracket. So as we can see, the solution seems to be invalid at first, but one cannot determine whether x is an integer or not, right? Because x, they're just saying, is a real number. However, it actually works because although x itself might not be an integer, it is very close to 1. So there are therefore 199 potential x. So I kind of racked my brain on this because I said, okay, this is great if x was specified to be an integer, but x is being told as a real number. But apparently, if you read this, we can assume that because x is very close to an integer, we just look at the integer values. And therefore, when you count up all of them, you get 199 such values. So therefore, number 25, the answer is C. How many sequences of zeros and ones of length 19 are there that begin with a 0, end with a 0, contain no 2 consecutive zeros, and contain no 3 consecutive ones? All right, well, this question, we've got a few scenarios here, and we're going to need to make a table and talk about them. Okay, so there's 19 slots, and we have to put either a 0 or a 1 in each of those slots. So we have to figure out how many zeros and how many ones. Well, they gave us a couple rules that you cannot put 0, 0, and you could not put 1, 1, 1, like that. So if I start off with a 0, my next number cannot be a 1. It cannot be a 0. It can be a 1. Okay, so 0, 1 is allowed. So I think the 0, 1, 0, 1 will be fine, like that. And here you go. Here's a string of 19 of these numbers. And this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, and obviously 9 ones. And there's only one way of making such a sequence. So that one is pretty straightforward. We're done with that. Now we want to see, okay, for the number of zeros, how many more can I put? Or how many less can I put? Can I put any more? Well, if I put a 0 anywhere where there's a 1, it fails the test because I can't have a 0, 0. So that means I can't put any more than 10 zeros. But I can put less than 10, I can put 9. If I have 9 zeros, then I have 10 ones because the total is 19. Okay, so now let's talk about this. I have 9 zeros, so 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, but how do I place those ones? I've got 8 gaps. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 of these gaps between the zeros. And I've got to place those 10 ones in those 8 gaps. But how do I do that? Well, there's 8 and there's 10 ones, so I'm going to have to double up on 2 of them. So for example, if I put 1 1 here, then I can put individual ones in all the others, and that'll add up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that's just one way of doing it. How many are the total number of sequences? Well, from the 8 gaps, choose 2 of those gaps to place those 2 1 1s. Got it? So in this case, for example, I chose those 2 gaps. But I can choose any of those. And then that's it. The other 6 gaps that will be remaining, you choose all 6 of those to place the 6 individual ones. And that takes care of the 9, 10 scenario. The next one is if you have 8 zeros, and then of course you would need to have 11 ones. So then we have 0, 0, 0, 0, 0, 0, 0, 0, 8 of those. And we got 1, 2, 3, 4, 5, 6, 7 gaps. So 7 gaps this time between the zeros. And we've got 11 ones. So how do I place 11 ones? Well, let's see here. I could put 1, 1, 1. But that's not allowed. I can't put 3 ones in a row. So I have to put individuals or just 2s, like 1, 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. Does that add up to 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So from the 7 gaps, I've got to choose 4 of those to place those 4 1 1s, these guys. And then from the remaining 3 gaps, I choose 3 to place the individual ones. Okay, that takes care of that. And then we have the last one, which is 7 and 12. Here I've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6 gaps. And the 6 gaps have to hold 12 ones, and there's only one way of doing that, by putting 1 1s in each of those gaps. Because if you put an individual, then the one will have 3, and that's not allowed. Okay, I think we're done. There's only one way of doing that. So now all I have to do is figure out these numbers. Well, this was just 1, and this was just 1. So 8 choose 2, I got to figure that out. And I believe 8 choose 2 is what, 28? 6 choose 6 is just 1. So 28 times 1, which is just 28. 7 choose 4, that is 35. And then 3 choose 3 is just 1. So it doesn't really matter. 35 times 1. So now the total number is this 1 here, plus that 28, plus that 35, and plus that 1. And that grand total is 65. And therefore, number 25, the answer is C. Let D and N denote the number of ways of writing the positive n as a product n is equal to f1 times f2 dot 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 until fk, where k is greater than or equal to 1. The f at I are integers strictly greater than 1, and the order in which the factors are listed matters. That is, 2 representations that differ only in the order of the factors are counted as distinct. For example, the number 6 can be written as 6, 2 times 3, and 3 times 2, so D6 is 3. What is D96? Okay, I wanted to give a little bit of a primer before I jump right into this question, and that is, how do we figure this out? Well, they gave us a nice example that D6 is 3, and they even showed us how. D6 is 3 because 6 can be represented as 6, or 2 times 3, or 3 times 2. And that is the only way I can break it up into a string of numbers where the product is equal to 6. So since there's only 3 ways of doing that, D6 is 3. All right, now I want to see, is there a relationship between different D's? So for example, if I have D12, can I write that as a relationship with other D's? Let's see. What is D12, for example? We can figure that out pretty quickly. It can be either 12 by itself, or it can be, let's see here, 4 times 3, 3 times 4, 2 times 6, 6 times 2. And I think that exhausts when k is 1, it's like this. But when k is 2, I think these are the only 4. And when k is 3, meaning you have 3 numbers, I think the only way is just all the prime factors, which is 2 times 2 times 3. So we have 1, 2, 3, 4, 5, 6. So are there any more? There should be. Ah, I see. This has iterations. 2 times 3 times 2, 3 times 2 times 2. Because they even tell me that in the question. Two representations that differ only in the order of the factors are counted as distinct. Okay, so that's why. So 1, 2, 3, 4, 5, 6, 7, 8. I got 8. So D12 is 8. Now, when you fiddle around with this, you hopefully will be able to conclude that D12 can be represented as the sum of the D's of its factors. So D6, what are the factors of 12? 6, 4, 3, 2. Right? 1 they don't want because they want F1 to be greater than 1. Okay, no problem. Now, D6 is 3. D4, I can easily figure that out. D4, I can either represent 4 as 4 or 2 times 2. So D4, there's only 2 representations, so D4 is 2. D3 is just a prime number, so there's only one way of writing it, and that's just 3. So D3 is 1. And D2 is also a prime number, so there's only one way of writing it, and that's just 2. Okay, 1, 2, 3, 4, 5, 6, 7. Ooh, 7. But the answer is 8. Well, here's the thing. You have to add one more. Why? Because that final one represents just the 12. This one right here. When it's by itself. That's why we have to add that one. So, it is indeed 1, 2, 3, 4, 5, 6, 7, 8. So, which is what we got. So, that's an important sort of conclusion to come to in this question. A bit challenging, I think. I do not think it's easy, especially when you have like 2 minutes on a math contest. All right, so what do they want us to figure out in this question? D96 right here. Okay, so I will do D96, and off we go. So D96, as we have previously concluded, will be a sum of the D's of the factors of 96, which are 48, plus 32, plus 24, plus 16, plus D12, plus D8, plus D6, plus D4, plus D3, plus D2, and as previously mentioned, we have to add on a 1 at the end because that represents the representation of 96 when we have just one number. All right, so here we go. Some of these we already know, right? D2 is 1, D3 is 1, D4 we had calculated as 2, D6 we had calculated as 3. So now we have to figure out all the other ones. Okay, so D8, well, that, in a very similar way, you just break it down instead of doing it the long way. D4 plus D2 plus plus 1. Remember, you have to put the 1 at the end. Don't forget that. So this is going to be just 2 plus 1 plus 1. And that is 4. So D8, put a 4 there. And now we have D12. And D12 is D6. D12 actually we just did. Yeah, we just did D12. So that was 8. Okay. I don't need to go through that whole thing then. It's just 8. So I did that in the primer. Great. So that's 8 right there. All right, moving right along. What's next here? D16. Okay, so D16 with our same sort of philosophy is the sum of the D's of the factors. So D8, D4 plus D2 plus that 1 at the end. So that's going to be 4 plus 2 plus 1 plus 1, and that is equal to 8. So D16 is 8. All right. So I think you get the hang of this. D24, that is going to be D12 plus D8 plus D6 plus D4 plus D3 plus D2 plus 1. And these numbers are 8, 4, 3, 2, 1, 1, and 1, and that is equal to 20. All right, so we got 2 more. Let's squeeze it in on the same page. So D32 is D16 plus D8 plus D4 plus D2, and then don't forget that 1 at the end. And this is going to be 8 plus 4 plus 2 plus 1 plus 1, and that is 16. So we are almost done. And then I just have to figure out D48, which is going to be D24 plus D16 plus D12 plus D8 plus D6 plus D4 plus D3 plus D2, and then don't forget that 1 at the end. And all of these guys added up, this is what D24 was 20, D16 is 8, and then D12 is 8, and then we have plus 4 plus 3 plus 2 plus 1 plus 1 plus 1, and that is equal to 48. Okay, that was the last piece of the puzzle, 48. All right, so now I just have to add up these guys, and when I do, I get 112, and that is the value for D96. So number 25, the answer is A. Let S be the set of lattice points in the coordinate plane, both of whose coordinates are integers between 1 and 30, inclusive. Exactly 300 points in S lie on or below a line with the equation y equals mx. The possible values of m lie in an interval of length a over b, where a and b are relatively prime positive integers. What is a plus b? On the AMC exams, graph paper is allowed, and so are rulers. So you will take your ruler and graph paper and try to figure out this question. And it's very time consuming, actually. I'm always amazed at how time consuming these questions are, because you have 3 minutes to solve it. So here we go. And here we go. It's a masterpiece, right? So let's explain this. We have all the plots here, all the lattice points, basically. And we have to see if we have exactly 300 points below the line y equals mx. Now, y equals mx, the solid line. We'll talk about the dashed line a little bit later, but let's just look at the solid line. The solid line is the equation y equals mx plus b. Now, since y equals mx plus b, when we draw it, we want 300 points, exactly 300, not 301, not 299, exactly 300. The total number of points, since it's a 30 by 30 grid, the total number of points will be 900. And we want 300, so basically we want a third of them below that line. So that means that most likely this is going to be a situation where m is rise over run. The run is easy, that's just 30. And the rise is going to be from there to there. And if you count those dots, it's 20. So the slope looks like m over 3. So that is what you call the lower bound. And then later we'll figure out the upper bound, but at least this is the lower bound. Now, we have to actually be convinced that this is indeed 300 points. We can't just guess. And the good news is you can do it pretty quickly. You can count the number of dots. So for here, it's 0. The number of dots here is 1, then 2, then 2, then 3, then 4, and then 4, and then 5, and so on. So I'll write them all out. And there you go. And we can add this up pretty quickly. It looks like every 3 we've got a situation where we have one number and then 2 of the next number. So we can easily just say 1 plus 2 plus 3 all the way until 20, because that would take care of these guys here. And then once those are taken care of, we're left with 2, 4, 6, 8, 10, 12, 14, 16, and 18. And we can add those up pretty quickly. So the sum from 1 to 20, well, that's just 20 times 21 divided by 2, and that's 210. And then these ones, you can easily manually add them up. And when you do, that's 90. So 210 plus 90 is indeed 300. So indeed, when we drew the line with m equal to 2/3, we got exactly 300 points below that line. Okay, so we're convinced that the lower bound is correct. Great. Now we need the upper bound. The upper bound is such so that the number still remains 300. So we got the lower bound, but then the upper bound is going to be open, meaning it won't touch it. It'll come close to it, but it won't touch it, because if it touches it, then we're going to end up adding another lattice points, and this will become 301. And we can't do that. We can't have 301. It has to be exactly 300. And that dashed line, I hope you can see it. It's right here. It represents the upper bound. And that upper bound, as you can see, touches this point. And if we included it, it would become one extra lattice point, 301, but we're not going to include it. That's why we're putting a curve here to show that it goes to that point, but it does not include it. Well, since it touches that point, we can easily use that to figure out the slope. The slope is just rise over run, right? Rise over run. And the rise looks like, well, we have to count it. Well, I already did. It's right there, 18. And the run is 28. So that slope, the rise is 18 and the run is 28. But here's the thing. This 18 was only until here. I have to include one more because that upper bound approaches that lattice point. So instead of 18 over 28, it's 19 over 28. And therefore that goes there. Now I know the confusing part is you say, well, if we are including that, then we're including one extra lattice point. So this 300 will become 301, right? How is that valid? Well, because we're not including that point. We're approaching it. And that's what that curve means, that we are not including. We're getting as close as possible to 19 over 28 for the value of m, but not including. All right, so that's about as best as I can explain it. So now we have to figure out the range. And the range is between 19 over 28 and 2/3. So we got to do this math here. And that looks like, if you do that, it's 1 over 84. And that is basically the interval. And it's in the form a over b, right? So this is my interval, range, whatever you want to call it. So a plus b would be just 1 plus 84, and that is 85. For this very challenging and time-consuming question 25, the answer is E.